Okay, so we've introduced the Galois group of an extension. We've proved that it is in fact a group. We're going to now collect some more examples beyond the example that we investigated as our motivating example. So we're going to compute the Galois group of C over R. So this is gamma of C over R. All right. So what does that mean? We need to take any automorphism that fixes R. And we need to try to figure out what actually it does set theoretically. It's automorphism fixing, R, not automorphism, pointwise. Okay, so an R automorphism, something that fixes R pointwise. Well, this is why we spent so much time working out set theoretic descriptions of our extensions, because we have to play with them, and we have to play with them, start playing with them right now. So what do elements of C look like if we want to view it as an R vector space? Elements of C look like x plus iy, right? So what must be true? Well, alpha, if it is such an automorphism, again, we don't really know anything about it besides it's compatible with addition, it's compatible with multiplication, and it fixes R pointwise. Well, since it's compatible with addition, we can break it up under addition. And since it's compatible with multiplication, we can break the second term up under multiplication. But x and y are, right, they're real numbers. So if my alpha fixes all real numbers, then alpha of x is x, and alpha of y is y. So what this is saying is alpha is determined by what it does to I. And so we saw this before a while back, and it's coming back again now. Now we're going to play with the fact that we know the minimal polynomial of I, and that will give us ideas as to what it should do to I. So alpha of I squared is alpha of I squared is alpha of -1. -1 is a real number, and alpha is supposed to fix all real numbers. So alpha of I must be a square root of -1. Why? Well, because when I square it, I get -1, according to this work. So there's two possible choices. It's either alpha of I is I, or alpha of I is -I. All right, the first instance, let me say that differently. This gives us two possible automorphisms. Now I'll explain what I mean by two possible elements of the Galois group in a second. So we get one of them that takes x plus iy and spits out x plus iy. That is, it doesn't move I. That's this first choice. And we get, let me write a better alpha, sorry. And we get an alpha 2 that takes x plus iy and negates the y part. So this alpha 1, we know this first guy, this is just the identity. And this one is complex conjugation. And those are the only possible R automorphisms of C. Those are the only possible automorphisms of C that fix R pointwise. Why? Well, we showed that they're determined entirely by what we do to I. Now, I write possible because just because we were able to say, hey, alpha has to send I to I or negative I, it doesn't mean that we actually have defined automorphisms. So just because we know that alpha of I is I or negative I, it does not mean that we actually get automorphisms. That is, our conditional was, if we had an automorphism, then it must do this. We haven't shown if it does this, then it is an automorphism. That's the converse statement, which is not equivalent to the original if-then statement, the original conditional. So we actually need to then check. We must verify we actually have automorphisms. This has to be done. We do not automatically know that alpha 1 and alpha 2 are automorphisms. Now, alpha 1 is the identity. We know the identity is an automorphism. Okay, so there's nothing to do there, but we don't automatically know in the general case that whatever we write down is going to be an automorphism. So it needs to be checked. That alpha 1 is an automorphism is fine. Is true. The identity is always an automorphism, period, in any category. Now, what about complex conjugation? Well, we've already seen complex conjugation is an automorphism. It was one of our examples. But let me remind you of another way of going about this that doesn't rely on that and relies on more of our expression of field extensions via polynomial rings, our description that way. So let me just say another way is to notice that the minimal polynomial of I is t squared plus 1 over r. And so we get this composite isomorphism where we take r adjoined t, we mod out by t squared plus 1, the minimal polynomial. We have this map that evaluates at negative I, and we also have sort of the inverse evaluation at I map, which would take us to r adjoin I. Now both sides of this are C, of course, because if you add in I, that's the same as adding in negative I. And so alpha 2 is first undo evaluating at I, and then evaluate at negative I. The evaluation maps fix R pointwise, and it's pretty simple to see. All they do is they interchange I with negative I. And that's all that alpha 2 does. So again, to prove that complex conjugation is an automorphism is fairly simple. We did it in chapter 1. But we can apply a slightly more highbrow technique that will generalize to other examples. And it's this composite picture that we've drawn a couple of times. So this is an automorphism of C. And so in particular, alpha 2 is in fact an automorphism. It fixes R. And so what do we get? Well, the Galois group of C over R is the identity and complex conjugation. Or if you want to use the alphas, it's alpha 1, alpha 2. Okay. Now, abstractly, as a group, when you conjugate twice, you get the identity. So abstractly, as a group, this is just Z mod 2. Or some people write it as mu2. If you want, you can do that as well. Or some people write it as C2. They all sort of mean the same thing, but slightly differently. And so that's our first, well, I guess our second example of computing a Galois group.